Hello children, how are you all? I hope all of you are doing really well. For those who don't know me, my name is Deepti, and for those who know me, hello again. Today we are going to explore an amazing tool that has changed the way we live, learn and play. Can anyone guess what it is? That's right, it's the computer, and I guess computer is one of the most interesting subjects, isn't it? So let's get started. Our today's chapter, numbering system. Okay, chapter profile, number system, conversion of other numbers to decimal number systems, conversion of decimal numbers to other number systems, and binary arithmetics. Okay, first brain boosting, write the correct numbers next to each Roman numeral. Okay, I guess everybody knows that. Okay, everybody is familiar about Roman numeral. Okay. In the early days, when there was no means of counting, people used to count with the help of fingers, stones, pebbles, etc. These methods were inadequate and had many limitations. To overcome these limitations, number systems were introduced. Do you know how do early people used to count? They used to count on fingers, okay? But there were few other methods also, like they used stones or pebbles to count, but there were some limitations with these counting numbers or with these methods, okay? So to overcome these limitations, then a number system was introduced, okay? Number system. A number system is a way of writing and understanding numbers within the computer system architecture. It helps us represent quantities and perform calculations using different rules and symbols. The value of each digit in a number depends on the following factors. Okay. First, the digit itself. Next, second, the position of the digit in the number. You know the position of the digit in the number, and the base of the number system. The total number of digits used in the number system is called its base or radix. Okay, both these terms are similar. Base or radix. The base is written after the number as a subscript, such as 20, whole bracket, and then 10. So here 10 is what? 10 is the base, okay, or you can say radix, right? Factboot. Aryabhatta, great mathematician and astronomer in India. He introduced the concept of zero, which is helpful in modern computer technology. I'm sure everybody knows that the concept of zero was given by India, and it was given by Aryabhatta, who was a famous mathematician and astronomer in ancient India. Okay? The number system is divided into 4 categories. These are binary number system, octal number system, decimal number system, and hexadecimal number system. Now let's learn about these number system in detail. First, binary number system. The binary number system is a method of representing numbers using only 2 digits, 0 and 1. It is also known as base 2, and it uses just 2 symbols. Each digit in a binary number is called a bit. Okay students, remember that in binary number system, we use only 2 digits, that is a 0 and 1, or here base is 2. Okay, and every digit in binary number is called a bit, B-I-T. Okay, this number system is used by all digital computers to convert the data input into its binary equivalent. Some examples of the binary number system are like 0100 whole twice, or you can say whole 2, and 101101 and whole 2. So 2 is base here. The binary number system is also a positional value system where each digit has a value expressed in powers of 2, right? In any binary number, the rightmost digit is called the least significant bit, that is LSB, and the leftmost digit is called the most significant bit, that is MSB. So, for example, 11010. So, 0 is the rightmost digit, so it is known as LSB, and 1 is the leftmost digit, so it is known as MSB. Okay, that is most significant bit. Factboot. Gottfried Wilhelm Leibniz, a German mathematician, is credited with the invention of the binary number system. So this German mathematician, whose name is Gottfried Wilhelm Leibniz, he was the inventor of binary number system. Okay. Next number system is decimal number system. The decimal number system is the most commonly used system for representing numbers, also known as base 10. Okay. So in decimal number system, base is 10. Okay. So it uses 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Each position in a decimal number represents a power of 10. Okay. Because base is 10. Right. Some examples of the decimal number system are 908 and base is 10, 230 whole twice and then 10, etc. Right? The decimal number system is also a positional value system. Like binary number system, decimal number system is also a positional value system. This means that the value of each digit depends on its position. Let us take an example to understand this. Say we have three numbers: 962, 694 and 529. The value of 9 in all three numbers is different. As you can see here, value of 9 in every number is different. Why? See, in 962, value of 9 is 900, so 900. Because 9 is at 100 place, so you can also write it like 9 into 100 and 9 into 10 raised to the power 2. Because 10 raised to the power 2 is 100. Then in 694, value of 9 is 9 tenths, because 9 is at 10th place. Or you can say, you can write 90, which is 9 into 10 or 9 into 10 raised to the power 1. In 529, value of 9 is 9 units, because 9 is at ones place, or you can say units place, which is 9 or 9 into 1 or 9 into 10 raised to the power 0. 10 raised to the power 0 is 1. Okay. The weightage of each position can be represented as follows. Okay. Next, octal number system. The octal number system is a base 8 system for representing numbers. So in this case, or in this number system, base is what? 8. So it uses 8 digits: 0, 1, 2, 3, 4, 5, 6 and 7. Each position in an octal number represents as power of 8, because base is 8, right? Some examples of the octal number system are 736, base is 8, 690, base is 8 and 115, base is 8, etc. The octal number system is also a positional value system where each digit has its value expressed in power of 8, as shown here. Here you can see, right, like 8 raised to the power 5, 8 raised to the power 4, 8 raised to the power 3, 8 raised to the power 2, 8 raised to the power 1 and 8 raised to the power 0. Next is hexadecimal number system. The hexadecimal number system is a base 16 system for representing numbers. So here, what is base? 16. So it uses 16 symbols, the digit 0 to 9 and the letters A to F, where A represents 10, B represents 11, C represents 12, D represents 13, E represents 14 and F represents 15. Some examples of hexadecimal number system are A, C, D and base is 16. A 14, base is 16 and 986, base is 16. Okay. The hexadecimal number system is also a positional value system where each digit has its value expressed in powers of 16 as shown here. You can see here, right? Now, conversion of other numbers to decimal number systems. We can convert other numbers like binary, octal and hexadecimal to decimal numbers by following these steps. Step 1, write down the number and its base. Step 2, multiply each digit by the base raised to the power of its position. Step 3, add the products to get the decimal number. Okay, so let's learn with the help of an example, okay, how to convert in decimal numbers. Okay, so binary to decimal, base 2 to base 10. Okay, so in binary number system, base is 2, you know that you have to convert into decimal number system, and the base of decimal number system is what? 10, right? So first, what will you do? Multiply each binary digit by 2 raised to the power of its position, starting from 0 on the right. Then add the results to get the decimal value. So finally, we will have to add the results so that we can get the decimal value. Okay, example is, see, 1011 base power is 2. This is the binary number system and we have to convert this into decimal. So How are you going to write it? 1 into 2 raised to the power 3. And 2 raised to the power 3 is 8. You know that? And 1 into 8 is 8. Now, next digit is 0 after 1, right? So, 0 into 2 raised to the power 2. And 2 raised to the power 2 is 4. You know that. But 0 into 4 is 0. Next, 1 into 2 raised to the power 1. So, 1 into 2 is 2. And 1 into 2 raised to the power 0 is equals to 1 into 1. Remember that, students. 2 raised to the power 0 is not 0. It's 1. Okay. So, 1. And now, add the numbers. Okay. Results. So, 8 plus 2, 10 plus 1, 11. Okay. So, 11 base power 10. Okay. Next, octal to decimal, base 8 to base 10. Now, in octal number system, base is 8 and we have to convert into decimal number system, okay, where base is 10. You already know that. So, multiply each octal digit by 8 raised to the power of its position starting from 0 on the right. Add the results to get the decimal value. Okay, students, steps are same, but the difference is that now we have to multiply each digit by 8 raised to the power of its position. Okay. For example, convert 157 base power 8 to decimal. So, we'll write 1 into 8 raised to the power 2, right? And 8 raised to the power 2 is 64. So, 1 into 64 is 64. Next digit is 5. 5 into 8 raised to the power 1 is equals to 5 into 8 is equals to 40. And then 7 into 8 raised to the power 0 is equals to 7. Okay. Now, add the results. 64 plus 40, 104 plus 7, 111. So, 111 base power 10. Okay. Next, hexadecimal to decimal, base 16 to base 10. Okay. So, what is the base of hexadecimal number system? 16. So, we have to convert 16 to 10. Okay. So, multiply each hexadecimal digit by 16 raised to the power of its position starting from 0 on the right. Okay. Again, the procedure is same. Okay. Add the results to get the decimal value. Okay. For example, convert 1a base 16 to decimal. So, 1 into 16 raised to the power 1 is equals to 1 into 16 is 16 and a into 16 raised to the power 10. Okay. Now, what is the value of a? Value of a is 10. So, 10 into 1 is 10. Okay. Now, add the values. 16 plus 10, 26 and 26 base is 10, right? So, crisscross time, you have to convert the numbers into decimal. Okay. Next, conversion of decimal numbers to other number system. Okay. Now, we will convert decimal to other number system, means decimal to binary number system, decimal to hexadecimal number system, right? So, we can convert the decimal numbers to the other number system by following the given steps. Step 1, divide the decimal number by the target base, that is 2, 8 or 16. Step 2, record the remainder. Step 3, continue dividing the quotient until it becomes 0. So, here we will have to divide and we will divide until the quotient becomes 0. Okay. Step 4, write the remainders in reverse order to get the converted number. Okay. So, decimal to binary, that is base 10 to base 2. Decimal numbers can be converted to binary by repeatedly dividing the number 2 while recording the remainder. Okay, so here we will have to divide by 2 because we are going to convert decimal to binary. That's why we will divide it by 2. Okay, so let's take an example to see how this happens. Example, convert 25 base 10 to binary. Okay, so divide 25 by 2. So, 2 12s are 24, okay, but here is 25, so remainder is 1. Then 2 6 are 12, 0 remainder. Then 2 3s are 6, 0 remainder. Then 2 1s are 2 and 3 minus 2 is 1, that is 1 remainder. And then 1, okay, this is your 5th remainder. Now, read up the remainders in reverse. Reverse means bottom to top. Okay, so we will write it as 1 1 0 0 1. Okay. Next, decimal to octal number, base 10 to 8. Decimal numbers can be converted to octal by repeatedly dividing the number by 8 while recording the remainder. Because we have to convert in octal numbers, that's why we will divide by 8. Okay, the procedure is the same. So, let's take an example to how this happens. Example, convert 239 base 10 to octal. Okay, so first we'll divide 239, okay, by 8. So here first remainder is 7, then second remainder is 5, and then third remainder is 3. Okay, now read at the remainders in reverse. So 357, this is the octal number. Okay, next decimal to hexadecimal number, base 10 to 16. Decimal numbers can be converted to hexadecimal by repeatedly dividing the number by 16 while recording the remainder. Again, the procedure is same. The only difference is that we have to divide the number by 16. Okay, let's take an example to see how this happens. So the number is 3479. So there are 3 remainders. First remainder is 7, second is 9, and third one is 13. But we will not write 13. Okay, 13. Value of D is 13. So that's why we'll write here D instead of 13, right? Now read it the remainders in reverse. So D97. Okay. Crisscross triangle, you have to convert decimal number which is given over here 9570 into hexadecimal. Okay. Next, binary arithmetics. The computer processor performs arithmetic operations only on binary numbers. Therefore, it's essential to understand binary arithmetic to comprehend how the processor works. Binary arithmetic includes all operations like addition, subtraction, multiplication, and division. Let's learn about them. Binary addition. The technique used to add binary numbers inside the computer is very easy and simple. This is performed similarly to addition with decimal numbers. So there are 4 rules of binary addition. Okay, see. If the value of A is 0 and the value of B is also 0, then A plus B, that is 0 plus 0 is equals to 0. So carry with no carry. Okay, now value of A is 0, value of B is 1. 0 plus 1 is 1 with no carry. Now value of A is 1 and value of B is 0. 1 plus 0 is 1 with no carry. Now value of A is 1, value of B is 1. 1 plus 1 is 1. Okay, not 2. Remember that. With carry of 1. Okay. So in fourth case, a binary addition creates a sum of 1 plus 1 is equals to 10. 10, not 2. Right? That is 0 is written in the given column and a carry of 1 goes over to the next column. Right? So let's understand it with the help of an example. See, these 2 numbers we have to add. 11101 plus 11111. Okay, so let's have a look. See, 1 plus 1 is 10. So we'll write 0 and 1 carry over. Again, 1 plus 1 is 10. So we'll write 0 only. 1 plus 1 and there is 1 carry. So we'll write 1. Then 1 plus 1 and there is 1 carry is 1. Again, 1 carry. So 1 plus 1 and then 1 carry is 1. And lastly, we'll write 1. Okay. Binary subtraction. In binary subtraction, a binary number of lower value is subtracted from the higher value. We know that while subtracting, always what is to be done? Lower value is subtracted from the higher value. So there are 4 rules of binary subtraction. So what are the 4 rules? Let's have a look. Value of A and B, 0. So A minus B, that is 0 minus 0 is 0 with no borrow. Value of A is 1, value of B is 0. 1 minus 0 is 1 with no borrow. Value of A is 1, value of B is 1, 1 minus 1 is 0 with no borrow. Now, value of A is 0 and value of B is 1. 0 minus 1 is 1. With a borrow of 1 from the next column, this makes it 10 minus 1, which is 1. Okay, so let's have a look. Example is there. We have to subtract 1010 from 1100. Okay, so 0 minus 0 is 0. Now, you cannot subtract 0 minus 1, okay, you cannot subtract 1 from 0, or if you remember this 4th rule, 0 minus 1 is equals to 1, but there is a border of 1, okay. So 10 minus 1 is 1 and 1, 1 minus 0 is 0 and 1 minus 0 is 0. So 0, 0, 1, 0 is the answer. Next, binary multiplication. Binary multiplication is similar to decimal multiplication. It is simpler than a decimal multiplication because it only involves zeros and ones. So there are 4 rules of binary multiplication. Okay, if the value of A and B is 0, so A into B is 0, means 0 into 0 is 0. Value of A is 0, value of B is 1. So 0 into 1 is 0. Value of A is 1, value of B is 0. 1 into 0 is 0. Value of A is 1, value of B is 1. So 1 into 1 is 1. Okay. Now see the multiplication. 1 into 0 is 0. 1 into 1 is 1. 1 into 1 is 1. Okay. Then 1 into 0 is 0. Again we'll write the same. Okay, and then add. So 1, 0, 0, 1, 0 is the product. Okay. Now binary division. Binary division is similar to decimal division. It is called as a long division procedure. So let's divide 11,010 by 101. Okay. So see the division. Okay. So we'll get the quotient of 101. Okay. And there is one more example here. Okay. Now revision time. The number system is simply a method to represent or express numbers. The most commonly used number systems in a digital representation are decimal, binary, octal and hexadecimal. These are the 4 number systems. Okay. The decimal number system is composed of 10 numerals. 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Means 0 to 9. The binary number system has a base of 2 with only 2 digits, 0 and 1. The octal number system has a base of 8. The hexadecimal number system has a base of 16. Binary arithmetic involves all operations like addition, subtraction, multiplication and division. So students, here comes the end of this chapter. I hope you have understood this chapter. Now you will do practice of the exercise.